All right, everybody. Let's do some chemistry. I know it's hard this time of the year. Focus. We've got a couple more chapters to get through, though. We can do it. And that's the incentive is that if we get through the stuff that we have to get through, we can do the stuff that's more fun, like nuclear chemistry. Jason? I'm gonna look at the schedule and figure it out, but we're probably gonna be covering stuff that's just gonna be shorter lectures. We probably won't have a lab next week. But I'll figure that out when I look at the schedule. And let you know. You're still coming to class, so you'll figure it out on Monday when I tell you, right? All right. So still going through some older quiz questions. Somebody asked about reaction types. Can reaction only be one type of reaction? Is there a limit to how many types of reactions they can be? Not really, although typically if it's a more complicated reaction that is multiple different types of reactions, we typically break it up as a series of reactions instead of just calling it one reaction. Although there is a pretty good example of a reaction that is, where do you go? That is both, or it's two reactions at the same time. Where did the video go? Basically, if you take copper metal and you put it in concentrated nitric acid, you'll make copper 2 nitrate, and you'll make NO2 as a gas, plus some water. However many waters we need to balance that. I think it's 2 waters. And I think there's a 2 there. What this reaction actually is, it's a combination of reactions because we can look at it and definitely see it's a redox reaction. What's our dead giveaway that it's a redox reaction really fast? Metals. What about metals? What does a redox reaction mean? Reduction is half of it, and oxidation. So when their charges are changing, copper is going from a charge of 0 to a charge of +2. So right away, we know this is a redox reaction. However, it also involves an acid, and it winds up making water. So we also have an acid-base reaction happening at the same time. And this is actually a fairly cool looking reaction. I had a good video, but then now it's trying to make me go through a paywall to see the video again. So we'll go with good old YouTube.
I normally show you science experiments that are fun and exciting to do at home.
So what happens if you put a penny in nitric acid?
When you add copper to nitric acid, it reacts violently, forming copper nitrate in solution and a thick red cloud of nitrogen dioxide gas. It looks really awesome, but this gas is highly dangerous. When you breathe it in, it forms nitric acid in your lungs, causing your lungs to fill up with fluid.
Super fun, right? Nitric acid in your lungs. We do that experiment at the college. We have to do it in the fume hood though, and since we only have one tiny fume hood here, we can't really do that experiment here. So come take Gen Chem at the college and you'll be able to do that one. And then we actually wind up going through a couple of sequential reactions and then reducing the copper back to being metallic copper at the end, and you get copper metal as a powder, which is kind of cool. And that nitrogen dioxide gas that you make is actually one of the main components of smog in some places. It's one of the reasons we have catalytic converters on cars with that have internal combustion engines, is to limit how much NO2 you make, because it's really, really bad for you. And that's one of the reasons why you can tell by the color of smog on a city where they get their gas to some extent, because different sources of petroleum are going to give you different mixtures in the gas. And so I believe was it Beijing that had like the reddish smog. But LA used to have that reddish smog too before catalytic converters were required in California. And Beijing also has a little bit of that too. So you're constantly being exposed to low levels of this gas that's producing nitric acid in your lungs, which is why having the Olympics in Beijing was kind of a problem for, marathon runners that had to run outside in that smog. It was less than ideal in terms of competition conditions. But this is just a good example of a reaction that is both an acid-base reaction and a redox reaction at the same time. We could probably break that down into two reactions, the redox reaction and then the acid-base reaction, but it's typically written as one reaction. But then as soon as you start looking at stuff like the citric acid cycle, then it's like, okay, well, it's an isomerization reaction followed by a reduction reaction followed by an acid-base reaction, as opposed to treating them all as one reaction. Usually it's a bunch of things happening in sequence, not all at once. All right. Other questions, kind of interesting. How long does it take us to take out to test new reactions? Not very long. As you have new reagents, you can make new reactions right away. Figuring out what you made takes a little bit longer. And if you're trying to do something like produce a product for sale or a medication, then a lot of times it's the testing that goes into making sure what you made is safe that takes longer, because that involves, double blind testing, long-term testing when you're talking about medications and things like that. So it's a lot of times it's the follow-up that actually takes a really long time if you're trying to bring a product to market. Yeah.
How would you never put these chemicals together before? How would you know that what you're creating prior to what you're creating it isn't gonna destroy the world?
You don't always. There were have you watched Oppenheimer? There were calculations that suggested that setting off the first atomic bomb at the Trinity test might ignite the atmosphere.
Yeah.
It turns out that they did the math wrong, but there was a reasonable chance to question that came right as they were about to do the test. And no, they double checked all the numbers, and that one person still thought he did the numbers right and was still like, no, don't do it, stop the test, all that. But then everybody else looked like, no, you slipped a decimal point there or something. I don't remember exactly what the error was, but there was some error that everybody else caught that this person wasn't convinced that was an error. But for the most part, we have a decent idea of what's going to happen before it happens. It's a little bit like doing a reasonableness check before you hit enter on your calculator. You should have a decent idea of what you're going to do, what's going to happen before you actually do it. In most cases, that's true. Even if you're doing a reaction nobody's ever seen before, you have an expectation of what's going to happen. It doesn't always match that expectation, but you have some understanding of what's going to happen, even if you then are surprised. If you want to talk about rates of reactions, how long does a reaction itself take? That's something where you need to take calculus and then take Gen Chem. I guess you can do it in either order, but talking about rates of chemical reactions is actually really interesting because you get to bring some of these calculus ideas in. And we typically measure rates of reaction in units that are in units of molarity per second, for instance. When you look at how many moles are reacting per second of reaction time. So you can actually get into some interesting units and some interesting math when you go that route too. One last note about getting products approved. There's a really good reason why it takes so long to get things approved. Sometimes turns out that there have been times when products get approved for sale in other countries, for instance, that wind up having the disastrous side effects that are totally unexpected. There's a molecule called thalidomide that gets used as a classic example of this. Thalidomide is a molecule that has some anti-nausea properties and seemed like it had very little other side effects to it. So they started producing it. It got approved in Europe for sale for treating morning sickness in pregnant women. Except it turns out that they were actually making two mirror images of the same molecule and prescribing them the same way. But the way the enzymes work, one of those had the anti-nausea properties. The other one actually really stunts tissue growth, which doesn't seem like that's that big of a deal if you're giving it to an adult. But when you're giving it to a pregnant woman, that's a big problem. So there was actually like 6 months, they didn't notice this until the baby started being born. And then somebody put it together that it was the thalidomide. And so there was about 9 months worth of children born in Europe where this was commonly prescribed that are, missing limbs, missing organs, have no lungs, depending on what tissue, what organs were developing when the mother was taking that drug. So it turns out that because there was one person in particular that really vetoed that product getting okayed by the FDA in the US. And that one person was the only reason why the US didn't have that same issue. She really took a lot of flack from industry leaders that were trying to produce this product that was going to make them millions of dollars, but she holds steady and it turned out to be vindicated by that. And it now turns out that thalidomide, the one that stunts tissue growth, that version actually has uses too. It got very, very villainized, but now they're using it for cancer treatments. Because what is cancer except tissue that you don't want replicating and growing? So they're starting to look at using that thalidomide in adults with cancer to slow tumor growth. So it goes to show that using there's no wrong drug necessarily. There's incorrect uses, or where the side effects are way worse than the original symptoms. But that's kind of a classic tale of how why we have government regulation. Because if we just let the chemical companies or the pharmaceutical companies have free reign with that, then it would have turned out very, very differently in the US anyway. As far as what the actual times are, now I don't think any pharmaceuticals get approved in less than about a year. The COVID vaccine was probably the most recent treatment that was expedited through the process because we kind of had a need for that vaccine as quickly as possible. They still did all of the testing. They just rushed it and they didn't wait for some of the more long-term results because they were looking at early indicators of what the expected side effects might be. So it still went through the same process, just much more quickly because there was such a need for it. All right. Let's do some practice with pressure versus volume. How did finishing up the charts yesterday go? Everybody got that under control-ish? The charts for the pressure versus volume and pressure versus 1/volume? Something like that. Quick reminder of where we started. This is our first simple gas law. Our first simple gas law, Boyle's law, was that pressure 1 times volume 1 equals pressure 2 times volume 2. For any gas, any enclosed gas that's at a constant temperature, if you change the volume, it changes the pressure. And we can predict what those changes are by using this equation. And so if you have a 750 milliliter bottle and it's sealed at 760 torr and kept at a constant temperature, if the volume then expands to 1.65 liters, what's the new pressure inside the bottle? So the way you think with these simple gas laws is it's always a before and after. P1 and V1 are your initial conditions. P2 and V2 are what we have after the fact. So in this case, you have to know 3 out of the 4 pieces or it doesn't work, right? So what's P1? 760 torr. So really the trickiest thing about this sometimes is figuring out what units go with what variable. But as long as you're paying attention to units and you know that P is pressure and that torr is a pressure unit, it's pretty easy to figure out what goes where. What's T1? Oh, sorry, we're not doing temperature. V1. 750 milliliters. What do we know from the after side?
That's the volume.
We know it has to equal, and we know the volume in liters. We know V2 is 1.65 liters. We're ready to just plug in and solve for P2? Not quite.
Solve for pressure for every liter.
We convert milliliters.
We need these two to match units. Doesn't matter what units you use for volume or for pressure, as long as they're the same before and afterwards. Otherwise, they're not going to cancel out properly. So then we can say 760 torr times 0.750 liters equals P2, that's what we're solving for, times 1.65 liters. So to solve for P2, we just can divide both sides by the volume, by V2, right? We should get something that's $345. 750's got 3 sig figs, so everything's got 3 sig figs. Because it's 760 torr, we're gonna assume that's exact because that's a standard pressure that we see all the time. But technically, yes, you don't know that for sure. So we would assume normally 2 sig figs. So as long as we're using these equations, we can pick any volume units we want because as long as they're the same, they're going to cancel out when we do the division, right? And same for our pressure units. We can pick any pressure units we want for this as well. In this case, it's not canceling out. That's going to give us our final pressure. But if we wanted our final answer to be in atmospheres, we could then convert it, or we could start by converting 760 torr to atmospheres, right? As long as you're consistent with these simple gas laws, it doesn't matter what units you use. So you just have to know, hey, millimeters of mercury, that's a pressure unit, or pascals, that's a pressure unit, or gallons, that's a volume unit. All right, any questions on this one? We're going to go through a whole bunch of, so this is the first example. It's called a simple gas law. We're going to go through a bunch of simple gas laws. And they're all going to work pretty much the same way. Figure out what variables you have, plug them in, solve for the one you don't have. It's a sort of math problem we call plug and chug. Okay, so we want it in PSI. How do we convert torr to PSI? We've got a bunch of standard atmospheric pressures that are all equal to each other. So if 760 torr is equal to 14.7 PSI, Just a conversion.
Like, is that like a real thing to happen? How the volume should be like,
So you could do like a piston, for instance, or you could think of it like a balloon. If you let a balloon expand, more often than not, it's actually the pressure driving the volume change rather than the other way around. So let's say we had let's say we took this bottle and we put it under conditions that caused it to expand to 1.65, and we wanted to figure out what the pressure was inside now that it's expanded. So it can be that the pressure is actually driving this, but it's actually easier to measure volume than it is to measure pressure.
there's no addition.
And this is a simplified version.
But like, would there be like.
We'll do some more examples. You'll see some, but this is an oversimplified version. Because a bottle doesn't just expand like that without pushing back against the other gas a little bit, right? A balloon is a better example, but even a balloon, you have to apply some extra force to get it to stretch, right? But if you can think of a balloon that started at 750 milliliters and then we climbed to the top of Talac and it expanded to be 1.65 liters. So what's the pressure at the top of Talac then? That's when we would use this. It's not actually, it's the change in pressure that's actually driving the change in volume in that case. But it's still sometimes easier to measure volume. So even though pressure is the actual cause, we might calculate it this way. All right, more questions on Boyle's law? Let's look at Charles' law again. We did this one the other day on the board because the slides went out on us. We saw that if we change the temperature of a gas, the volume is going to change as well. If you increase temperature, volume goes up, and it goes up in a straight line, but it wasn't proportional. What does proportional mean in math terms? Close. It means you can write a simple proportion. It basically means you can do a one-to-one conversion. And basically, in math terms, in graphical terms, if it's proportional, it means that the line goes through the origin. Because if the line goes through the origin, you don't have an intercept on your conversion. Right? If you have an intercept, a y-intercept on your line, it's not proportional. So if we wanted it to be proportional, we could write temperature in Celsius to temperature and volume here. We would get something like, okay, well, our volume is equal to some constant, the slope, times our temperature plus another constant, right? But that's not a very easy conversion. Mathematically, these functions work a lot better. We get simpler functions like this when we have things that are proportional to each other. The other factor, when things are proportional, you can say things like, I doubled the temperature. What happened to the volume? It also doubled. We can't say that if there's a y-intercept. Doubling the temperature does not necessarily double the volume on a graph like this, with units like this. So what they did was they basically just shifted 0 over. They just said, we're going to set 0 temperature to be where there would be 0 volume. Yeah, and that's where Kelvin comes from. Basically, just okay, track this line backward until it hits the x-axis. What's the x-intercept for this? When they solved for the x-intercept, was at negative 273.15 Celsius. And that's where our conversion from Celsius to Kelvin comes from. Instead of saying our temperature in Celsius, we put our temperature in Kelvin, because then, wrong computer, we get a graph that looks like that. So a difference of 1 degree Kelvin is the same as 1 degree Celsius. It's the same slope of the line. We've just shifted it back so that there is no intercept. Which again, kind of feels like cheating, a little bit like our assume X is close to 0. But it just means that you need to be in the right units for this next simple gas law to work. So if we don't have an intercept, I just erased what I'm going to use here in a second. If the y-intercept is 0, this term goes away, right? And we just get that volume is equal to a constant times the temperature. Which if we rearrange that to set it in a similar form here, we can say, okay, well, for any system of gas at a constant pressure, we can say volume 1 over T1 equals our slope, which equals volume 2 over T2. So basically we get almost the same form here. It's just, it's volume over temperature, not volume times temperature. Because they're directly proportional, not inversely proportional. Pressure versus volume is inversely proportional because when you doubled pressure, volume got cut in half. So one goes up, the other one goes down. Volume and temperature are directly proportional because you double one, the other one doubles. Which also seems kind of weird because that seems like if you expanded the volume, if you double the volume, the temperature has to double too, which seems counterintuitive. But it's because usually it's going the other way around. You double the temperature, the volume doubles. That makes a little bit more sense. So the way, so that's Charles' law is V1 over T1 equals V2 over T2. So let's do an example of that one. A sealed 1 liter system is heated from 22 Celsius to 51 Celsius at a constant pressure. What's the new volume? We know V1?
Yeah.
Yeah, 1.0 liters. Do we know T1? 22 degrees Celsius. But remember that this equation only works if our temperature is in Kelvin. So we just have to add 273 to it. Remember our conversion from Celsius to Kelvin? Temperature in Kelvin is equal to temperature in Celsius plus 273.15. So that's going to make it 295. Then we know T2 is 51 Celsius, which is going to be 324 Kelvin. How many sig figs do we keep when we're doing a Celsius to Kelvin conversion? It's an addition, right? So keep the same number of decimal points or keep the uncertainty in the same spot. So this is plus or minus 1 because the uncertainty is in the ones place, right? The last reported digit is in the ones place. So we're going to keep our uncertainty in the ones place. So we gain a sig fig. Remember, with addition and subtraction, we're not counting sig figs, we're counting uncertainty. We keep the uncertainty the same for addition and subtraction. So 22 Celsius, that's plus or minus 1 Celsius. When we add our 273 to that, we're gonna keep it plus or minus 1 Kelvin. 51 is plus or minus 1 Celsius, the way it's written. So our answer in Kelvin is also going to be plus or minus 1. We haven't thought about addition and subtraction sig figs for a few minutes, right? A little bit of a review. So if we want to know what the new volume is, plug these in, solve for V2. So 1.1, right? We're only going to get to keep 2 sig figs now anyway. So 1.1 liters. So we went from 22 Celsius to 51 Celsius. That's more than doubling our temperature in Celsius, right? But our pressure, our volume did not double because Celsius is not absolute absolute temperature. If you want to double the temperature to see the volume double, you have to do it in Kelvin. It didn't double in Kelvin. Exactly. That's my point. Doubling the temperature in Celsius doesn't double the real temperature. The real temperature is Kelvin. Maddie? So it means proportional. So it's not saying that it's equal. Proportional means that it's a straight line and it goes through the origin, like we were talking about. And that's the mathematical symbol for proportional. It kind of looks like a Greek letter alpha. So, but the other way of writing that is saying that volume is equal to a constant times temperature. That's the equivalent statement. Right, so simple gas laws, relatively simple. You've got to know 3 out of the 4 pieces for them to work. So figuring out based on the problem what goes where is the trickiest part. So know your units, know what type of unit is a pressure versus a temperature versus volume. And they're not too bad. It's a small nitpicky note. 295 Kelvin was equal to 22 degrees Celsius. Technically, we don't write degrees Kelvin. Degrees, the degree symbol means that you took an established distance and you chopped it up evenly into a certain number of points. So degrees Celsius was taking the melting point of ice and the boiling point of water and then just evenly chopping it up into 100 sections. When you take that approach, that's when you use the degree symbol. Kelvin isn't done that way. Kelvin actually has 0. And it doesn't have a maximum. We didn't say, okay, 100 Kelvin is this and 0 Kelvin is that and chop it up evenly. So we don't use the degree symbol. Everybody's still going to know what you mean. But if you see something written like this without the degree symbol, that's still Kelvin. DM? I took too long. All right. There was something else I was going to say, and I took too long for myself too. So I'm sure it'll come back to me. There is a Fahrenheit version of absolute temperature. So the way we just took Celsius and then we just shifted it over, You can do the same thing with Fahrenheit and you get Rankine, which is a capital R is the symbol for it. Nobody uses it. Not even in the US. Anybody who's doing things with absolute temperature in the US that uses Kelvin. Maybe there's like one or two engineering firms somewhere in the US that use Rankine, but it's worth knowing that it exists. Nobody really uses it because if you're doing calculations where you care about that, you're in Celsius already. So Kelvin is the much more common absolute temperature unit. All right, our next simple gas law is just as simple as this one. And we actually don't even need to do the experiment for this, which is good because this involves keeping a fixed volume and changing the temperature. That's not really a good idea to do in practice, right? Does anybody ever seal the container and then change the volume? Ooh, it doesn't go well. I mean, I guess if you're expecting it and you're appropriately attired in PPE, then that's one thing. But basically, something's going to explode.
That would happen because of lighter.
Yes. You can also do that with old CRT TVs. They're vacuum tubes, right? And so but they still have a little bit of gas in them. And so they're this nice enclosed gas. If you get it hot enough, it pops. You can do the reverse of this too. If you take an oil can, if you put a little bit of water in the bottom and get it boiling, and then screw the lid on really tight and put it in ice water, it crushes the can. So we don't necessarily want to do those experiments where we're saying keep it as a fixed volume and change the temperature because things go wrong. So what we do instead, go ahead. I still do need to bring the blast, and actually the one where it gets crushed is okay. And there's actually a pretty cool video. I'll find that video in a second. They do the same thing with a 55-gallon drum. And it collapses all at once. It basically, you can hear it kind of groaning, and then all of a sudden the air pressure crushes it. But before we get there, we need to know what law we're looking at there. And basically, we can just do this from classical geometry, from Euclid's axioms. We can say if A is equal to B and B is equal to C, A is equal to C. Makes sense, right? It's like one of those things it's so basic you barely remember learning it in grade school because it's like, why are you telling me this? This is obvious. Sometimes that's what an axiom is, though. Turns out we can do the same thing with proportionality. We can say if A is proportional to B and B is proportional to C, then A is proportional to C. That is a little bit more useful in this case because we have volume is proportional to temperature and pressure is proportional to 1 over volume. You basically do a quick substitution and get the pressure version of the same equation. So all you're doing basically is swapping out pressure for volume in each of these. So P1 T1 equals P2 T2. So if you double the absolute temperature, if you double the temperature in Kelvin, you double the pressure if you're at a fixed volume. So that's why this is so dangerous, is because every container is going to have a set pressure where if you get beyond that, the container ruptures. One of the ways that this happens is, and I do not recommend doing this, and none of you are 18, so you can't go buy dry ice at the grocery store anyway. But if you take dry ice and a little bit of water and you put it into a soda bottle, and then you seal it, you wind up with the temperature then coming up, and the dry ice not evaporates, it sublimates and adds more gas molecules to the system. Turns out that soda bottles are rated for about 4 atmospheres of pressure. And once you get past that, they pop. But 4 atmospheres of pressure is kind of a lot. So they actually, the technical term for that is a bomb. So don't go do this.
Seriously.
Right? It's the sort of thing that me and my delinquent friends did in high school. And did wind up with the cops called on us more than once. Set off car alarms.
What would be?
Nobody lost any eyes, but a piece of a bottle went flying right by my friend's face and cut him on the cheek. And then we started borrowing safety goggles from the chemistry lab. So he let us check them out. It was technically borrowing. But it's like, you know, it seems like, oh, it's just dry ice and water. How dangerous can it be? It can be pretty dangerous. He didn't need to get stitches, but he did have a scar for a couple years on his cheek. So be careful. Don't do that. And if you were going to do something like that, be very careful. Yeah.
Let it go down the sink.
Yes. It's a very good, you don't put dry ice down the sink because either you're going to freeze the water and cause your pipes to burst, or you're going to generate a whole bunch of gas in a confined system. And when you do that in a plumbing system, what that looks like is it vomits up everything that's in the pipe out one of the other vessels, one of the other drains. So with dry ice, it's less of an issue. It's more about don't rupture the pipes with the dry ice. But with cleaning products, so just another good PSA, never mix cleaning products, especially things that go down the drain. If you mix cleaning products, you can wind up with some really nasty reactions. Like if you do something like, wipe down the bathroom, the bathtub with ammonia, and then there's this stubborn stain, so you get bleach out. Ammonia and bleach makes a version of mustard gas. Yeah, and it's definitely pay attention, never mix cleaning products. The other one that happens about once a year, you see somebody tries to fix a stopped drain with a crystal drain cleaner. And then and then it doesn't work. They leave it there. And then somebody else comes back and tries to fix it later with a liquid drain cleaner. Well, the crystal drain cleaner is sodium hydroxide usually, and the liquid drain cleaner is concentrated sulfuric acid. When you mix them together, you get a really, really hot acid base reaction that boils water and causes everything to explode out of the drain. So I think it was just a couple of years ago, there was a janitor in the Central Valley that died because somebody treated a stuck drain with crystal drain cleaner, and then he came along with liquid drain cleaner and it blew up into his face.
That just sounds like aggressively effective.
They're very effective. You just need to be paying attention and not mix them unless you know what you're doing. That's why you also, you don't have two people working on the same problem that don't know what the other one's doing. Right? So you communicate. Label things. All right. So let me.
Please buy me dry ice.
Really, college company for dogs, to make a flat points, but really tricks that allow me to step it.
If you're looking for a good idea for your senior project, you can do random chemistry demonstrations like this as long as you tie it to some sort of community service aspect.
What is your school education?
Yeah. That's exactly what I did for my senior project. Actually, I worked with a community college professor to do some testing but I just did a cool demonstration as my final product for my.
Takes a couple minutes. Just bring up the ice unit with your hand out. It's so loaded.
So those things are designed to resist pressure change, right? So it took a while. But when it went all at once. You can hear it just before it happens. It like groans and then implodes. In more topical terms, a poorly designed submersible underwater would go through a similar situation, which when you're a mile under the water and can't reach the surface, that's a lot of pressure really fast. So think that, except more extreme. I believe that they're pretty sure that they knew it was about to happen, but it would happen really quickly. Kayla? It was. I mean, I'm not a medical doctor, so the exact physiology of what would happen is a little bit different, but basically, yeah, it's like getting hit by a bus, basically. Except from all sides at the same time.
It's possible. Like difficult, but they could be like halfway, like just be like still, I guess, like conscious, like.
No, it would have been too much pressure too fast for something like that. Alexander? So it turns out, have you ever done the experiment where you take an empty soda can and stand on it? If you're really, really careful, you can stand on an empty soda can. But as soon as you poke the side just a little bit, you have one spot where it gives, the whole thing crushes. So it's basically they had one seam fail, and then that caused a catastrophic failure of everything. Right? And that's basically what happened there. Asen? It would be the opposite in space. You would wind up, so Apollo 13 is a good example, right? If you let the gas expand against no exterior pressure, you get an explosion. If you have extra pressure on the outside, you get an implosion. Right? So space is more likely to go the other way.
That point of weakness called like the critical failure architecture.
It's similar. So I believe, again, not an architect, so I might not have the language down, but usually that's referring to a specific material, like, solid oak with no flaws in it has this much pressure it can take before it fails.
Yeah.
But they might have a similar term for like a combined where everything's built together. Like, where is it going to give first?
Yeah. It's one building in New York where they built it on like this joists were on the sides instead of the corners.
Yes.
Like accounted that with the wind, so they had to do 20 billion loads.
Right, exactly. If you don't think things through and you get too creative with your architecture, then the engineers have to come in and fix it later. Is there another question over here? It's useful to know how it happens so that you can prevent it from happening. I mean, I'm sure you can find. Yes, actually, the second atomic bomb that was dropped on Japan was an implosion style where they took a whole bunch of shaped charges in a sphere and fired slugs of plutonium at each other. in such a way. So they aimed all of the explosions inward, to get everything compressed evenly from all sides at the same time. And they called that an implosion style fission device. So basically, yeah, so when you want to apply force, high force levels of forces evenly in all directions, if you can arrange things to do something similar to this on purpose. I can't think of another example off the top of my head, but I'm sure it's been used in other spots as well.
I can't wait to ask you.
All right. So everybody feel like, oh, froze it. We killed PowerPoint today. Try that again. All right, so far, all of these different simple gas laws have one thing in common, and that's that two variables are changing, but other variables are remaining constant. Right, so in this case, V1 over T1 equals V2 over T2. That only works as long as the pressure is being held constant. And that's the no lid. That doesn't work, right? And the other, really, if I can get on this now, there it goes. Maybe. No, we really did kill it.
That's not how the dance goes.
All right, so is there another variable that's being held constant too? Think about the video we just watched. They had to put the cap on it. Why did they have to put the cap on it? But the volume was being held constant until it wasn't. The amount of molecules. We all of these, if you think back to all these practice problems we've done, they all started with here's your initial conditions and then it's sealed. Right? So that the number of molecules doesn't change either. But that means, so we really have four variables at play here. Number of molecules, pressure, volume, and temperature are all going to play a role together. As long as one of them gets held constant, we can actually use a combined version. These. So basically, we do the same logic as we used to get here. We can actually make a combined version. So the combined gas law basically takes all the simple gas laws and puts them together. What is it? So what is the other thing that's being held constant here? What Diego just said. Molecules. Balloon can be treated as a closed system, i.e. constant number of molecules. If we're not looking at a closed system, or if a chemical reaction is happening inside a closed system, that's actually what's going on with the dry ice bomb. Is you're actually generating CO2 gas molecules as the dry ice sublimates. So this is one version of the combined gas law. It's not my favorite version though. Version on the periodic table or on your equation sheet looks like this. These are all four variables that go into describing a gas. These are all the things that can change about a gas. The pressure can change, volume can change, temperature can change, the number of molecules can change. If you can describe all four of these variables, you're describing almost everything about that gas, other than what it is. Right, and so the reason this is the version on the equation sheet is because this has all of the other gas laws built into it. This has all of the gas laws built into it, because if anything is staying constant, it's the same on both sides, right? If number of moles is the same on both sides, if N1 is equal to N2, what happens algebraically when we multiply both sides by N1? P1 B1 over N1 T1 equals P2 B2 over N1 T2. If these are the same, then I can just multiply both sides by N1 and it goes away. If temperature's also being held constant, T1 and T2 are the same also, right? And then we're just left with the first simple gas law we started with, P1 V1 equals P2 V2. Right, so this version has all of the simple gas laws in it. Anything that's not changing, you just cancel it out on both sides.
So you can just, you don't really have to use that simple gas law.
Correct. Which is why this is the only one that's on the equation sheet. Right, because this is all of them. What happens if you're holding three variables constant? Then nothing's changing. If you hold three variables constant, if moles, temperature, and volume are all being held constant, your pressure's got to stay constant as well. No way to change the pressure without changing at least one of these other variables. I mean, that's not the way I write tests, but in theory, somebody could ask you to explain something like that. Not in this class. Although maybe, and now I'm thinking about it, maybe I do want to write it. No, I wouldn't write a question like that. I don't like trick questions. There will be a quiz this weekend. Basically do some simple gas law calculations and turn it in. Right? Nothing too tricky. There's one more aspect of this that winds up being significant. If all of these things are used to describe a gas, every gas can be described as the same ratio. Pressure of any gas times volume of that gas divided by the temperature of that gas divided by the number of molecules in moles will always give you the same constant. Every system of gas. This is actually one of those fundamental constants of the universe. The behavior of matter in the universe is such that every gas system gives you the same ratio of pressure times volume over moles times temperature. We call that R. For any gas, pressure times volume divided by moles times temperature equals capital R, which we call the ideal gas constant. So this is actually included in the middle here as well, right? But nobody really likes dealing with fractions when you don't have to. Do you? I mean, almost nobody wants to deal with fractions if you don't have to. So if you rearrange this, you get the one gas law to rule them all. PV equals nRT. So this is called the ideal gas law. It really just comes from combining all the simple gas laws into one. Right? And so this is a really useful way to describe a gas, because most of these things you can actually measure. R is always the same constant. It's on your conversion sheet. R is always 0.08206 liters times atmospheres over moles Kelvin. A pressure times a volume divided by moles divided by Kelvin. This isn't the only value for R, because it turns out for all the simple gas laws, we could pick any pressure unit we wanted, right? As long as we were consistent. In this case, we need the pressure units. We need all of our units to match the value of R we're using. There's other values of R. If you wanted to know a value for R in torr instead of atmospheres, you could look at that up. Only one value of R, well, two values of R are on your conversion sheet. But if you look up ideal gas constant on Wikipedia, there's like 3 pages of R values just in different units. It's all the same constant with just different units. If you wanted to have an R value in PSI, gallons, moles, Rankine, there's a value for R for that. But why? So it's usually easier to just take everything and put it in liters, atmospheres, moles, and Kelvin. And then you don't need to worry. Then you only need to have one of these memorized. Not that you need to have it memorized anyway. It's on your conversion sheet. All right, so let's do an example. These are all, well, relatively close to real numbers. I made them up, but they're all reasonable numbers. Scuba tanks are rated to have a pressure of 200 atmospheres. So if a scuba tank goes past the point of failure, you really have a problem. Because remember, my dry ice bomb example was only about 4 to 5 atmospheres of pressure, and it caused the problem. So if you haven't watched, here's your fun homework for the weekend. If you haven't watched the movie Jaws, you should watch the movie Jaws. It's a classic. And it has a very pivotal scene with a scuba tank and it failing and what happens. So if you haven't seen that, go watch that. You can tell your parents it's homework. As long as you also do your quiz.
Critical failure.
Critical failure, exactly. It's an engineering problem. So the scuba tank has a volume of 15 liters and is rated as filled to a pressure of 200 atmospheres at 22.5 Celsius. How many moles of gas are in the tank? Is there anything really tricky about this? Plug it in, solve for moles. You just need to make sure you get your units right. And I just erased it, but I'll rewrite the liters, atmospheres, moles, Kelvin. I know some of you don't like to write all your units all the time because it feels like a waste of time. It's not in this case. Even though this unit doesn't make any sense on its own, it's worth writing because it's going to remind you to do any conversions. Because what if I gave you the pressure in PSI instead of in atmospheres? Until you write this out, you might not remember that you're supposed to be in atmospheres, right? So your units all need to match up for this equation to work. And writing out your units is the way you remind yourself of that. So pressure is 200 atmospheres, volume 15.0 liters, temperature 22.5 Celsius, which means 295.6.7 Kelvin. R is a given. R is always the same. Solve for N. 200 atmospheres times 15.0 liters over 0.08206 liters, atmospheres, moles, Kelvin times 295.7 Kelvin. Plug and chug. As long as you can do your arithmetic on your calculator, then you should be good to go. See, so if I'm remembering correctly, that's gonna be, it's what, about 10 moles? Two hundred times 15 is gonna be 3,000, right? Divided by 300. So that's gonna be about 10. That's divide by 0.08, it's close to multiplying by 0.1. So maybe about 100. I slipped a digit in my head. 123? Excuse me. Destiny?
Oregon.
R is the ideal gas constant. It's always the same for every gas. And it's not called the ideal gas law because it's perfect or it's the best to use in every situation. It is, when in doubt, use the ideal gas law. It's assuming that the gas is ideal. An ideal gas has two assumptions. Last concept for the day. Ideal gas assumes that if you got down to 0 Kelvin, it would have 0 volume. But what happens to everything before we get to 0 Kelvin? Everything. Now, if you took water and you tried to take water vapor down to 0 Kelvin, what happens before you get there?
Everything freezes.
Phase change, everything freezes. And at the very least, everything liquefies. So we're assuming nothing's going to go through a phase change in order to use this. This ignores any phase changes that might happen. So assumption one, and the way we write that out is assume no intermolecular forces, which we're going to define next week. But basically, it's the forces between molecules. It's exactly what it sounds like. If you don't have any attractive forces between the molecules, it'll never form a solid or a liquid. Solids and liquids only occur because the molecules stick together when they slow down enough. So, including phase change. The other one is a little bit, it's not necessarily as easy to see. What else would happen? So even assuming no phase change, if we tried to press down on a gas until we got to 0 volume, even if we could apply an infinite pressure, let's say we could apply infinite pressure, and it's not going to go through a phase change, there's still something else that's going to take up space. You still can't get a gas down to 0 volume, because the molecules themselves take up space. Asen? If you what? So if you actually converted all, so now we're talking about nuclear reactions but in theory, yeah, you could, that would be the exception. If you were able to convert the mass of the gas all the way to energy instead of matter, but then you don't have any moles anymore. So then basically everything goes out the window because you don't have any matter. If you don't have any matter, we can't measure things like, how do you measure temperature of something that doesn't have matter? Turns out you can't. If you don't have matter, you can't have a temperature or a pressure or a volume. So we're assuming gas molecules have 0 volume. Turns out these are decent assumptions under most conditions. If you actually look at atmospheric pressure, if you think about a gas molecule as being about the same size as a person, gas molecules, it would have to travel on average about the distance from here to Jupiter before it ran into another gas molecule in terms of proportion. So basically, a gas is almost entirely empty space. So for the most part, this is a decent assumption. The volume of a gas molecule is so tiny compared to the volume of the container that we can effectively say it's zero. Until we hit a phase change, or until we get to such a condensed system where your gas molecules actually take up a significant chunk of the volume. And we actually have a version of PV equals nRT that allows us to account for both of these, but it's a lot more complicated and you have to look up specific values for every gas. So it's not all that useful. But we'll talk about that next week.
That's great.
All right, so there will be a quiz this weekend. I'm probably not gonna be able to sit down on my computer and write it until after 5 today. So check it later tonight or tomorrow. And then I'll see everybody on Monday.
Every day, you guys come back here really quick. I want to